Before we consider how we might explain the strength of metallic bonding, it's worth having a quick recap of what metallic bonding is and its structure. You may recall from a previous video seeing a GIF that looks something like this. And here we can see a lattice of positively charged ions and delocalized electrons moving freely across that whole structure. Of course, because this is metallic bonding, this occurs between metal atoms. And given the low electronegativity value of metal atoms, they lose their valence electrons in order to form the structure above. Metallic bonding itself is defined as the electrostatic attraction between the lattice of positive ions and the delocalized valence electrons that are moving across the structure. And as an extra useful term to be aware of, we consider metallic bonding as non-directional because these electrostatic forces of attraction between the ions and the delocalized electrons are happening in all directions. Let's now consider how we might compare the strength of metallic bonding in different metals. The most useful data to compare the strength of metallic bonding in different substances is to look at the melting and boiling points. If we find that one substance has a higher melting or boiling point than another, this indicates that there must be greater forces of electrostatic attraction between my ions and delocalized electrons in that structure. Of course, if there are greater electrostatic forces of attraction, we consider that as stronger metallic bonding. So, which factors do we consider in order to explain differences in the strength of metallic bonding? The first factor to consider is the charge on the positive ions in the lattice. And this is also related to the number of delocalized electrons that there will be. The second factor is to consider the radius of the positive ions in the lattice. So let's now see if we can apply these two factors to an example. Let's compare sodium and magnesium metal. Here are the values for melting point found in the data booklet. And clearly you can see that magnesium metal has a significantly higher melting point, and we need to be able to explain why that is. In order to do so, let's start by drawing a structure for each of those metal substances. Because sodium is in group 1, it's going to have one valence electron, so when it loses that valence electron, we're going to form positive ions with just a single positive charge. In this diagram, I've got 12 positive ions, and given that each of them has lost one electron, there should be 12 delocalized electrons, symbolized by the negative sign in the space between the ions. If I compare this to magnesium, which is in group 2, it has 2 valence electrons, so when it loses both of them, each atom will become an ion with 2 positive charges. And you'll notice because each of those 12 atoms lost 2 electrons, we now also have twice as many delocalized electrons compared to the sodium. The other thing you might notice in this diagram is that the radius of the ions is smaller. Again, you can find that information in the data booklet or simply in your knowledge of moving left to right across a period normally leads to decreasing size. Let's now refer to the two factors at the top of the page and see if we can explain why magnesium has a much higher melting point compared to sodium. In terms of factor 1, we can see that magnesium has double the charge on those positive ions in the lattice and also double the number of delocalized electrons. This means that there will be much stronger electrostatic forces of attraction between the ions and the delocalized electrons, leading to a much higher melting point. In terms of factor 2, we also noted that magnesium ions have a smaller ionic radius compared to sodium ions. And this means that those delocalized electrons can actually get closer to the nuclei in the magnesium ions and again feel a greater force of electrostatic attraction. So in this example, both factors are leading to greater electrostatic attraction in the magnesium metal compared to the sodium metal, and this is why it has such a higher melting point. Let's now compare sodium with another metal in the same group, and actually let's consider potassium, which is below sodium in group 1. Potassium has the symbol K, And if I look in the data booklet, I find that it has a melting point of 63.38 degrees. So let's now draw the structure of potassium metal and compare it to that of sodium to try and explain why it has a lower melting point. Let's first consider factor 1. Well, because potassium is also in group 1, it has one valence electron, so when each atom loses that valence electron, we end up forming positive ions with a single positive charge. And this is exactly the same as sodium, so factor 1 here actually makes no difference to the melting point. So if factor 1 makes no difference to the melting point, let's have a consideration of factor 2. And you'll notice that in the drawing of the structure of potassium, the radius of the positive ions is much greater than sodium. This is because potassium is below sodium in group 1, therefore has more energy levels containing electrons, so a much larger radius. In comparison, sodium has a smaller ionic radius in its ions, and therefore the delocalized electrons in the structure of sodium metal can move closer to the nucleus of those ions and will feel a greater electrostatic force of attraction. So in this case, factor 2 helps explain why potassium has a lower melting point than sodium. In IB chemistry, these are the only two factors that we need to consider when looking at trends in melting points for metals. Let's now try and summarise the key points from this video. Firstly, the strength of metallic bonding can be quantified by comparing the melting points or boiling points of different metals. And when explaining differences in those melting or boiling points, we need to consider two factors. The first factor is the charge on the positive ions in the lattice, and this is related directly to the number of delocalized electrons in that structure, or you could talk about electron density in that structure. Of course, if we have a greater magnitude of charge on those ions and more delocalized electrons around the structure, we will see greater electrostatic attraction and therefore stronger metallic bonding. The second factor we need to consider is the radius of the positive ions in the lattice. And if we find a smaller ionic radius in those ions, this allows delocalized electrons to move closer to the nucleus, causing greater electrostatic attraction and again stronger bonding. And that's pretty much it. Hopefully this video is of some help.